Okay, the last chapter, chapter 13, is on fancy regression, where I'm going to show you that the simple linear regression model can actually be quite powerful. And the first vignette here will be on log and log-log transformations. So I'm just going to jump right into R, and we're going to look at this pickup data that you can download on the book webpage. And we're going to look at a couple different ways across the vignettes of this chapter. But here, let's look at the columns of this data frame. It has information about the year of the manufacture of a pickup, the number of miles it has on it, the price it's being advertised for on Craigslist, and then the make. Right now we're just going to look at year and price. So let's plot pickups year and pickups price. And then let me make sure you can see that. Okay, so you should be able to see that plot. So the price of the pickup is higher on average if the pickup is newer, if it has a later manufacture year. So this is just visualizing. I can fit a simple linear regression model. I'm not going to use the by hand stuff that we did in the vignette for chapter 7. Instead, I'm going to use the LM command in R, which is explained in the book in chapter 7. So you got to go take a look at that, where you can put the Y value, so that's pickups price, on the left of this tilde, and then you can fit a linear regression model like that, and it'll tell you what the estimates of the slope and intercept are. And you can also get some more information from the summary command that includes t-statistics and so on. And I'm going to talk more about that a little bit later. But for right now, what I want to focus on is the estimated line, which you can put on with the AB line command and give it the output of the fit that you get from the LM command. And when I look at this fit, I see something that's pretty good but not perfect. What I see is that I'm generally under predicting for low years, over predicting for middle years, and under predicting again for high years. So there's some pattern left over. Another good way to see that is with what's called a residual plot. If I plot pick up same X, but then I look at the residuals. So remember, residuals are E, which is Y minus Y hat, where Y hat comes from the fitted line. We did talk about that in chapter 7. Okay, and then I can put a horizontal line with 0 on there, and you can see that I've got positive residuals generally, and then negative residuals generally, and then positive again generally. So I'm not extracting everything that I could out of these data by fitting a line to them. We can work around that by transforming variables. I'm going to start with transforming y with the log. But you can also do this with the square root. I'm not going to do it in this video, but you can check it out more on that and other possibilities in the book. So I'm going to take the logarithm of pickups price, which is my response variable, and I'm going to add that to the data frame. I'm going to call it L price because it's the logarithm of price. And then I can do a fit that I'm going to call L fit with the LM command, and I'm going to do L price as my response, and the same X, which is pickups year. I didn't run the command before it. Okay. I've got to make sure I do data, and I don't need the pickups here. Year is fine, just like we did before. Data equals pickups. Okay, got it this time. So let's look at the visual of that. Plot L price as the X, and then pickups, no, year is the X, L price is the Y. I think you can already see in this relationship that it's going to be better fit by a line, which I can then put on the plot. So to me, this looks a lot better. And if I look at residuals from the LFIT, I do plot pickup year LFIT residuals. Pickups. Got it that time. To me, I don't see that same kind of pattern. There's nowhere in the inputs where I'm systematically over or under predicting. So I think that this is a better fit. So what are we doing? Let me go back to the whiteboard. Okay, so we are fitting a nonlinear model. We are looking at a model that models the logarithm of y with a linear equation. If I exponentiate both sides of that, so that would get rid of the log, and this is only approximate. You have to look at what's called Jensen's inequality to get this exactly right, but I'm exponentiating both sides, and I've got an e to the beta 0. Remember, when you exponentiate through a plus, it becomes a product. So I've got a nonlinear model. So a nonlinear fit with a simple linear model through the log transformation of the response y. After you have fit a transformed model, it's helpful to back transform, especially for visuals. Just imagine yourself in the shoes of your client. They gave you some data, and you start talking to them about linear relationships on logs of that data. They're not going to be able to understand that. People aren't good at thinking about what's going on in log space. So it's really helpful to back transform. Let me show you what I mean by that. So visualize back on the original data scale. Okay, so we can put our plot pickups year, pickups price. Okay, so there's the data. I got to reveal that for you. So we looked at that once before, and now I'm going to make a prediction with LFIT. So what I need to do is I need to make a grid. This is the same way we did prediction in chapter 7. I made a grid that goes from 1990, well, let's do 1989. And then let's go to 2008, or let's do 10, and then length equals so now I've got my predictive grid that I'm not going to use the formulas from chapter 7 because that'd be a little tedious. I'm just going to use the predict function, which will take my fit. I'm using LFIT because I like that better. I like to call this P or sometimes LP. And then I need to give it new data, a new data argument. And you want to give it X, but you want it to tell R that you're using years. So you do data frame year equals XP. So I'm giving it year variables in this grid, and it's my new data for the prediction. And then if I want a predictive interval, I could say interval equals prediction, or you could get a confidence interval if you want to with interval equals confidence. Okay, so I should be able to run that, and now I can put some lines on this plot. For example, I can get P1, that's going to give me the fit, but that's the fit of the logarithm of y, so I need to exponentiate it to undo the logarithm. So need to back transform my log y prediction. And then I can get the predictive interval by doing the other columns of what comes back out of P. This should be the lower part of the interval, and here is the upper part of the interval, a 95% predictive interval. Isn't that cool? First time I saw something like that, I was like, whoa, look what you can do with these tools. So yeah, that's the kind of basic idea of a log transform. Now I want to tell you about the log transform. So I want to introduce another data set here. Here is another data set that you can download from the book webpage. I call it confood, or confoods sometimes, read.csv, confood.csv. Again, you download this from the book webpage. And what it has is just two columns. So it has the price of some canned food that's sold at a supermarket from a company called Consolidated Foods, and how many units were sold at that price at the particular supermarket. Okay, so let's visualize this data. I want to type up here. Visualize data, plot, confood, price. So this time price is the x. Just imagine that the more you charge for something, the less you sell. And the amount you sell, that's the random quantity in this case. Confood sales. Okay, so this is what those data look like. It doesn't look like a linear relationship. So probably I'm going to need to make a transformation. Now before I talk about the log transform and why that makes sense, I want to go back to the pickups example. The transformation here, remember we transformed the y variable, which is on the y-axis, and we took the logarithm. The logarithm is a function that treats small numbers differently than large numbers. So it squishes the large numbers, it brings them down. It doesn't squish the small numbers as much. And if you look at this data, we have more data, more small y values, more values less than halfway. Say if this is halfway, looks like 2/3 or maybe even 3/4 of my data are below the kind of halfway level on this axis, whereas 1/3 of it is above the halfway level, just in terms of the magnitudes on the y-axis. So I call that bunching. I'm bunching in the y-axis, and when I take the logarithm, if I go back 2 more panels, I kind of fix that. The midway point here is now close to 50-50. About half of the data is below the halfway point, just in terms of the scale on the y-axis, and about half of it is above. So I have bunching in the y-axis in this pickup data. Well, in the confood data, I have bunching on both axes. Look, if I draw the halfway point here, I've only got like 1 point above it, and the rest of them are below on the y-axis. But on the x-axis, a similar thing is happening. If I draw a line at the halfway point, which is at about 0.7, there are more data points to the right than there are to the left. Just eyeballing it, I've got a kind of 2/3, 1/3 split. So I actually have bunching on both axes. So I'm going to write that out here. So I have bunching on both axes, so I could try the log on both axes. Okay, so what I mean is I'm going to do L price is log of food price, and L sales is log of food sales. This time I'm not adding it to the data frame. You can do it however you want it. And then I'm going to do an L fit. Well, let's visualize that. So plot L price, L sales. Okay, so that's what that looks like. Look how it's better. It's more plausibly linear. Okay, so plot L price. Oh, I already plotted it. Now let's do the fit. So L fit, LM, L sales, twiddle, L price, and then AB line, L fit. That looks like a pretty good fit to me. Yeah, so what have we done? What have we fit? It's probably time to go back to the whiteboard just for a second. So now consider that I'm modeling the expected value of y as a function that looks like this, clearly a nonlinear function. You could call this a multiplicative model. But if I take the logarithm of both sides, I'm going to get log a. Don't forget your rules of logarithms. Products become sums, right? And if I call this an intercept, and I call, well, this b a slope, and then this is my new x, so I've got a new y, this is my ly and my lx, then when I fit this log-log model back on the original space, I'm really fitting a nonlinear multiplicative model. So a log-log model is appropriate whenever quantities, by that I mean x and y, are linearly related on a multiplicative or percentage. Right? If you think about percents a little bit, they're really about multiplying scale. And in fact, in that context, an estimated slope, beta 1 hat, in a log SLR has a special name, is known as elasticity, which is an econ term that you can read more about in your econometrics books. So why is an elasticity interesting? It's because this estimated slope tells you the percent change in y given a 1% change in x, back on the original scale of the data. So if I look back at my fit, and I just inspect the coefficients of that fit, I can see that the slope is like -5. So this tells me that for every 1% increase in price, I see a 5% decrease in sales, which totally makes sense. You charge more, people are going to buy less. And if I want to, I can look at standard errors and t-statistics. Again, you can use what you learned in chapter 7 and do this all by hand, but the estimates here are shown in this table, and the standard errors on those estimates are shown here. And here we have t-statistics for, this has t-stats and standard errors, and t-stats for testing the null hypothesis of 0, either for the intercept or the slope. So here, a t-statistic for the null hypothesis that beta 1 is equal to 0 is big in absolute value, so the p-value of that test is small. So we know that there's not a 0% relationship with this elasticity between price and sales. But what we might want to test, that the elasticity beta 1 is equal to -5 or not. So I could take my estimate. Remember, test statistics are always estimate minus 1 to know divided by standard error. So I could take the estimate, which is -5, and minus my 1 to know, which is well, the other one's -5.14, and then -5, and then divide by the standard error, which I can grab from the table here, and this gives me a t-statistic. So that's my t-stat, and then I can do 2 times pt minus abs t-stat, and then it would be n minus 1 degrees of freedom. N would be the length of L price. Okay, so I cannot reject the null hypothesis that the elasticity is 5%. All right, let me wrap up here. Again, don't forget to provide visuals back on the original scale. Okay, so I want to end by doing that. I want to make a predictive grid that goes from the smallest price. Well, I want to make it back on the original scale. So let's do sales price, max sales price, length equals 1,000. So I'm making my grid. Oh, it's not sales, it's confood. Okay, and then I can do predict with lfit, new data equals, but now I've got to give it transformed versions of that grid. So I'm going to give it L prices that are log of xp. And then interval equals prediction. Okay, so that worked. And then I can make my plot on the original scale, which I did up here. Maybe I'll prevent myself from messing up. Oh, maybe I didn't. I thought I did. Oh, here it is. Okay, here's that plot. I don't think you can see it, but I can reveal it. So there it is. There's the plot on the original scale. And now I'm going to do lines, but I'm going to give it the original grid that I put the log on before I put it into predict, and I'm going to take what comes out, but I'm going to remember to undo the transformation on the y. Okay, so there is that line. It's got some curve to it. We'll do the same thing for the error bars that we get forming 95% predictive intervals by grabbing the other columns of the P matrix, but I'll change the color and the line type. So there's the lower one and then the upper one. So kind of cool. Other benefits to doing these transformations, especially transforming the y variable. If you look at a fit of a linear model, let's go back to the pickup one just because it'll be a little bit cleaner. We've made more plots of that one. So here's the original fit of the pickup data. In this straight line, eventually as we get to older and older trucks, we're going to predict negative, right? Any line, any straight line eventually goes negative. But it doesn't make much sense to predict a negative price for a truck unless someone's going to pay you to take it away. But I don't think that happens very often. But when we make the transformation and do the fit there, you can see that this has got curvature. Because we're exponentiating, you never get a negative prediction, not for the prediction itself or for its error bars. As the trucks get older and older, the prices get smaller, but they decrease the amount by which they get smaller, and they always stay positive because an exponential never has a negative output. Same thing for sales. You wouldn't want to predict sales going negative, and with this curvature that we get by doing a log transform and then untransforming with an exponential, we never predict something that's negative. So the log and the log-log transformation is really cool, and the log-log is particularly cool because it has this nice percentage interpretation through elasticity.